Welcome to Cosmic Origins Revealed, where we explore the cutting edge of space science and cosmology. I'm your host, and today we're talking about something extraordinary. Something that might fundamentally change everything we thought we knew about the universe. You see, in the past year and a half, we've witnessed what some scientists are calling a potential paradigm shift in cosmology. The very foundations of our understanding of dark matter and dark energy, these mysterious substances that supposedly make up 95% of everything, are being shaken. And I'm not exaggerating. We're talking about findings from the world's most sensitive detectors, revolutionary new particle candidates, and theories that challenge whether dark matter even exists at all. So buckle up. Today, we're diving deep into 4 major developments that are keeping physicists up at night. Let's start with what might be the biggest bombshell. Dark energy, that mysterious force driving the universe's accelerating expansion, might not be constant. It might be weakening. This discovery comes from DESI, the Dark Energy Spectroscopic Instrument, operating at Kitt Peak National Observatory in Arizona. And when I say this instrument is impressive, I mean it. Picture 5,000 robotic eyes collecting light from millions of galaxies across more than 1/3 of the entire sky. In March 2025, the DESI collaboration released their latest results based on 3 years of observations, nearly 15 million galaxies and quasars spanning 11 billion years of cosmic history. And what they found has the potential to rewrite cosmology. According to the standard model, what we call lambda CDM, where lambda represents the cosmological constant, dark energy should be, constant. It's been described as the energy of empty space itself, unchanging throughout time. One number, simple, elegant. But DESI's data is telling a different story. When the collaboration combined their galactic map with other measurements, the cosmic microwave background, supernova data, and gravitational lensing, they found something unexpected. Dark energy appears to have been stronger in the early universe and has been getting weaker over time. Professor Mustafa Ishaq Boushaki from the University of Texas at Dallas, co-chair of DESI, put it bluntly. With a 4.2 sigma significance, I think we are getting to the point of no return. Now, in physics, we typically need 5 sigma. That's about a 1 in 3.5 million chance of being a statistical fluke to declare a discovery. At 4.2 sigma, we're at about 1 in 40,000. Not quite definitive, but substantial, really substantial. Here's why this matters. If dark energy is weakening, it can't be Einstein's cosmological constant. Instead, it might be what's called a scalar field, something more dynamic, something that evolves. And here's the kicker. If dark energy continues to weaken, the universe's fate changes. We've long thought the universe would expand forever, getting colder and emptier until every star burns out and every atom is separated by unbridgeable gulfs, what's called the Big Chill or heat death. But weakening dark energy opens other possibilities. If it weakens enough, matter's gravitational pull could eventually win. The universe could stop expanding and start contracting, leading to what scientists call the Big Crunch. Don't worry, if this happens, it's at least 20 billion years away. Your weekend plans are safe. But Stacy McGaugh from Case Western Reserve University summed up the excitement. If true, it would be the first real clue we have gotten about the nature of dark energy in 25 years. The team will continue collecting data through 2028, aiming for 1,000 days of observations. Every new data release will either strengthen this finding or see it fade away. Either way, we're in for quite a ride.
Okay, so dark energy might be changing. But what about dark matter? That's the stuff that supposedly makes up about 27% of the universe's mass energy content, 5 times more than all the normal matter in stars, planets, and us. For decades, one of the leading candidates has been WIMPs, weakly interacting massive particles. These theoretical particles would barely interact with normal matter, maybe 1 interaction per kilogram of material per year. And to catch something that elusive, you need detectors that are equally impressive. Enter LUX-ZEPLIN, or LZ for short, operating nearly a mile underground at the Sanford Underground Research Facility in South Dakota, an abandoned gold mine. The detector's heart is 7 metric tons of ultra-pure liquid xenon, cooled to about minus 178 degrees Celsius, surrounded by layers of shielding and 17,000 light-detecting photomultipliers. In August 2024, the LZ collaboration released results from 280 days of data collection, their most comprehensive search yet. And the result? Nothing. Well, not quite nothing. They saw 335 nuclear recoil events, the kind that a WIMP collision would produce, but that number matches exactly what they expected from background radiation. Traces of radioactive isotopes like lead-214, cosmic rays that make it through their shielding, even radioactive decays inside the xenon itself. Dr. Amy Cottle from University College London, who led the WIMP search analysis, explained, "We've demonstrated how strong we are as a WIMP search machine." And she's right. This null result is actually incredibly valuable. LZ has now set the world's most stringent limits on WIMP properties, constraints that are nearly 5 times better than previous experiments. They've ruled out WIMPs with spin-independent cross-sections above 2.2 times 10 to the minus 48 square centimeters for a 40 GeV per c squared mass. To put that in perspective, that's 0.000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000000 is their attention to detail. Deep underground, they're shielded from cosmic rays. Their attention to detail. Deep underground, they're shielded from cosmic rays. Their xenon is ultra-pure to minimize radioactive backgrounds. They even use a technique called salting, adding fake WIMP signals to the data during collection, which are only removed at the very end. This prevents unconscious bias from creeping into the analysis. Hugh Lippincott from UC Santa Barbara said, "If you think of the search for dark matter like looking for buried treasure, we've dug almost 5 times deeper than anyone else has in the past." But here's the thing, they're not giving up. LZ will continue collecting data until 2028, aiming for 1,000 days total. And they're already planning the next generation, XLZD, which will combine the LZ and Xenon NT collaborations into a single, even more massive detector. Scott Kravitz, LZ's deputy physics coordinator, emphasized, "If WIMPs had been within the region we searched, we'd have been able to say something about them. We know we have the sensitivity and tools to see whether they're there as we search lower energies. The WIMP parameter space is shrinking. Soon, there will be nowhere left to hide."
So if WIMPs are getting squeezed out, what else could dark matter be? Well, here's where things get really interesting. In September 2025, physicists from the University of Warsaw and the Max Planck Institute for Gravitational Physics proposed something radically different: super-heavy, electrically charged gravitinos. Wait, electrically charged dark matter? Doesn't that violate everything we know? Not quite. Let me explain. Gravitinos are theoretical particles from supersymmetry. They're the supersymmetric partners of gravitons, the particles that supposedly carry the gravitational force. Traditionally, gravitinos were thought to be very light, nearly massless particles. But Christoph Meissner and Hermann Nicolai took a different approach. Working from n=8 supergravity theory, a framework that attempts to unify particle physics with gravity, they showed that the math actually predicts 8 different types of gravitinos. And get this, 2 of them would have electric charges of plus or minus 2/3, like quarks, and masses near the Planck scale. We're talking about particles with masses around 10 to the 18th giga-electron volts. That's about a billion times heavier than a proton. Now, you might be thinking, charged particles? Wouldn't we see them glowing in space? Here's the clever part. These gravitinos would be so incredibly rare that they wouldn't shine. The researchers estimate maybe 1 gravitino per 10,000 cubic kilometers in our solar system. Despite their charge, they're effectively dark because there are so vanishingly few of them. And because they're so massive and charged, they would leave traces as they pass through matter, faint trails of ionization and light. Which brings us to the exciting part, detection. China's Jiangmen Underground Neutrino Observatory, JUNO, is scheduled to begin operations in late 2025. It's a 40-meter spherical vessel filled with 20,000 tons of liquid scintillator surrounded by more than 17,000 photomultipliers. It's designed to study neutrinos, but according to the recent paper in Physical Review Research, it might be perfectly suited to catch gravitinos too. Adriana Kruk and Mikhail Lesiuk from the University of Warsaw ran detailed simulations showing exactly what kind of light trail a gravitino would produce as it passed through JUNO's detector. The signal would be unique,
Nothing else would look quite like it. The U.S.'s Deep Underground Neutrino Experiment, DUNE, could also search for them. Herman Nicolai put it this way: the common expectation is that dark matter is made up of an elementary particle that interacts with ordinary matter almost exclusively by the gravitational force. But the present proposal goes in a completely different direction. If gravitinos are detected, it would be more than just finding dark matter. It would provide evidence for physics at the Planck scale, energies we can't reach in any particle accelerator. It would be a bridge between quantum mechanics and gravity. That's revolutionary.
Now, let's talk about the elephant in the room. What if dark matter and dark energy don't exist at all? I know, that sounds wild. But hear me out, because there are serious scientists exploring exactly this possibility. The main alternative is called MOND, Modified Newtonian Dynamics. Proposed by Israeli physicist Mordechai Milgram back in 1983, MOND says that for very small accelerations, smaller than about 10 to the minus 11 times Earth's surface gravity, Newton's laws simply don't work correctly. Gravity behaves differently. And MOND has had some impressive successes. It predicts the rotation curves of galaxies with remarkable accuracy, often better than dark matter models. It predicted the external field effect decades before it was observed, and it doesn't require invoking invisible matter we can't detect. In July 2024, Case Western Reserve University researchers published findings that galaxy rotation curves remain flat for millions of light years, much farther than expected if dark matter halos had finite size. Tobias Mistelli, using gravitational lensing data, found that this behavior matched MOND predictions perfectly. Stacy McGaugh said it plainly: either dark matter halos are much bigger than we expected, or the whole paradigm is wrong. But MOND has problems, big problems. For one, it's struggled to explain the cosmic microwave background, that ancient light from the Big Bang, until October 2021, when Konstantinos Skordas and Tom Zlosnik published REL-MOND, a relativistic version of MOND that does match CMB observations by adding a field that acts like dark matter on cosmic scales, but modifies gravity on galactic scales. It's complicated. Some say too complicated. And in 2023, a study of wide binary stars, two stars orbiting each other at large distances, found that their orbits follow Newtonian gravity, not MOND. The measurement ruled out MOND at 16 sigma. That's pretty definitive. But even more radical ideas are emerging. In March 2024, Rajendra Gupta from the University of Ottawa published a paper claiming the universe might have no dark matter or dark energy. His CCC plus TL model combines covarying coupling constants, where the forces of nature change over time, with tired light theory, where light loses energy as it travels. Gupta's model suggests the universe is 26.7 billion years old, nearly twice the conventional estimate, and that what we attribute to dark energy is actually just the weakening of natural forces as the universe expands. So where does this leave us? Well, in October 2025, Gupta published follow-up work analyzing galaxy rotation curves with his model. He claims it explains the observations without needing dark matter at all. But here's the reality. The mainstream cosmological community remains unconvinced. David Spergel from the Flatiron Institute called REL-MOND Baroque. Most physicists argue that dark matter models, despite their challenges, still explain more observations more simply than alternatives. Tessa Baker from Queen Mary University of London put it well. If dark matter detectors continue to come up empty, then we may see increased interest in this family of modified gravity models. The search continues.
So here's where we stand at the end of 2025. Dark energy might be evolving, changing the ultimate fate of our universe. WIMPs are being systematically ruled out, narrowing the possibilities with unprecedented precision. Gravitinos have emerged as a radical new dark matter candidate, possibly detectable in the next few years. And alternative theories are challenging whether we need dark matter at all. What's remarkable is that we're not stuck in stalemate. Every experiment, every new data set, every theoretical breakthrough is pushing us toward answers. We're either going to detect dark matter directly, find compelling evidence for modified gravity, or discover something completely unexpected. Adam Rees, the Nobel laureate who discovered dark energy's acceleration, said about DESI's findings, "If true, it would be the first real clue we have gotten about the nature of dark energy in 25 years." 25 years, a quarter century of waiting, and now, potentially, the drought is ending. The universe is speaking to us through the data, through the silence and detectors deep underground, through the rotation of distant galaxies, through the faint light from the Big Bang. We just have to listen carefully enough to hear what it's saying. Thanks for joining us on Cosmic Origins Revealed. Until next time, keep looking up and keep questioning everything.